Good afternoon. I am Emanuele, I represent the Italian team, and today I'm going to talk to you about our solution on the screaming balloon problem. The problem states that if you put a X nut in a balloon, it's possible to make it scream by giving a certain rotational movement, and it asks us on how do the characteristics of the sound produced depend on the important parameters of the system. So let's see how the sound is made. We know that the sound is produced by the hertz between the rolling edges of the nut and the flat and elastic surface of the balloon that flexes and returns into its original position. So, in order to study the phenomenon, we used 6 different hexagonal nuts, electronic caliber, in order to measure with precision the length of the side of every nut. A balloon that was inflated into 2 different shapes that we assumed spherical. For the first one, we used a first-hand method in which we took a nylon stretch of about 56 centimeters of length, found a circumference, and then inflated the balloon inside of it. So the error on the circumference value is quite big. While for the second circumference, we used a different method. We carved a circle inside a card box, measured its diameter, measured 4 of its diameters, and then mediated them in order to obtain circumference. And so the error resulted in being smaller compared to the first one. We then took many registration of the sound produced by the nut, and using a program we took a number of consecutive periods of revolution. We took a number of consecutive periods. We then mediated them in order to obtain a mediated period, and then evaluated the main frequency of every system, of every of the 12 possible configurations. In blue are the results obtained for the first circumference, and in orange the results for the second. I evaluated the main frequency using a basic formula which states calculates the frequency as the circumference over the length of the side of every nut, obtaining the number of hits, and then divided this time by the period, and I plotted them with the respective trend lines. Seeing a possible similarity between the trend lines, I took the y-axis of the first results and I transported it on the right side, so that I could compare both the trend lines, and it's visible that they follow a similar path. So, seeing this similarity, we wanted to obtain more precise values of the. Here are reported the values of the frequencies for both the circumference and the length, and under the tables are reported the equation for both the trend lines. Seeing the similar path for both the trend lines, we wanted to obtain a more specific formula in which we use the circumference of the balloon, the length of the side of every nut, the width of the nut, and the period of rotation. And starting from a normal relation for a tangential velocity, we derived it, obtaining a final relation for the frequency, in which the minus L square root of 3 pi over c is the contribute made by the nut. So then I recalculated the frequencies, replotted them, retransported the y-axis on the right, and obtaining a more similar path for both the trend lines. Here are again reported the values, and if you take a closer look at the first and the fifth series of numbers, and the third and the sixth, since we can approximate the first length of about 5.7 10.7 millimeters, and the fifth to about 10.911, we can see that they are about one half the other. The fifth one is about double the first one, and if we could look at the relative frequency values, we see that the frequency relative to the first is about 500 Hz, while the fifth one is about 250, kind of half. The same goes for the second circumference, about 280, about 140, and for the third and the sixth, they are not really. The sixth one is not really comparable to the double the third, but the values are still quite related. So in order to verify this, not to see, if it was not just a case, we tried to vary the first formula, the frequency formula, by doubling the length of the side of the nut, obtaining a new frequency that goes where the part of minus d pi over c, in the limit of the width of the nut being very smaller compared to the circumference, we can neglect this part, obtaining that the main frequency goes by 1/2 the original frequency. If we triple the length of the nut, the same result goes, we obtain a similar result where the frequency goes by 1/3, and we halve the nut, the length, the side of the length of the nut, the length of the side. You obtain that the frequency goes as twice the original frequency that I reported here as n0 equals the circumference per square root of 3 over period per width of the nut. So as a conclusions, if we take a relook at the problem, at the main question of the problem that states on how do the characteristics of the sound produced depend on the important parameters of the system, we can say that the important parameters are the length of the nut and the circumference of the balloon, since the speed. I forgot about the period. I'm sorry. Where here? Here. We took 7 periods and mediated them. This procedure was repeated many times for every nut in order to have periods for every nut that were comparable to each other. So the frequencies are calculated via periods that are very similar to each other, not equals but similar to each other. Or otherwise I couldn't have plotted this graph. So to the conclusions, yeah. Parameters are the length of the nut and the circumference. Since the speed, the rotational speed is not important in my study, since I took values that all held same period. And in order to refine our model, we obtained that the frequency is so inversely proportional to the length.
Thank you.
Good afternoon, ladies and gentlemen. My name is Irina. I'm from Ukraine, and I'm happy to be an opponent on the problem number 9, spinning balloon. Thank you, dear reporter, for the work done. Let's analyze it. Your task was to find the characteristics of the sound that is produced by a spinning balloon, depending on the important parameters of the system. Your report will be organized as a qualitative part and the experimental part with some introduction of the theory. In the qualitative part, firstly you described us your mechanism of the sound generation, that is due to the heat of a hex nut with the walls of the balloon. It is very good. You well understood the mechanism of the phenomenon. However, you explained only the carrier frequency of the sound. And if you noticed during your experiment, a series of frequency is generated, so maybe it would be better to explain more deeply this phenomenon. And also you neglected other different sound mechanism generation. Maybe there is some noises, some friction, some deflection of the rubber membrane, etc., etc. But unfortunately, you neglected this mechanism. In the theoretical part, you found the carrier frequency of the sound due to the heat of the hex nut, and you listed as the parameters that you variated. It was the circumference of the balloon and the length of the side of the hex nut. However, you haven't obtained theoretical result for the spectrum, for the energy distribution by frequencies, and you haven't done, unfortunately, any prediction for other results besides the carrier frequency. You described only one characteristic of the sound frequency and no loudness, etc., etc. You theoretically haven't done a different parameter variation. You described only the circumference and the length. However, there is inelastic properties of the rubber. There is a velocity of rotation and many parameters, and it would be very interesting to discuss it during the polemics. And also, you haven't obtained the spatial distribution of the sound, because the sound depends on the point in which we observe it, and it's also a physical point in this problem. In the experimental part, you described as the experimental apparatus. You had different dimensions of the hex nut and the different balloon circumferences. However, your parameter variation was very small. There were only two circumferences on the ball, so it's very difficult to understand what is really the dependence on these parameters. And also in the experimental plot there was no error, so it is hard to understand what is the inaccuracy of the experiment, what is the impact of human factor. You didn't show us your experimental setup, how do you rotate the ball maybe by your hands, so there is some deviation, some frequency, etc. And I think that the errors are very important in this problem. Also, you don't show us the spectrum, so the energy distribution for frequency. You only showed us the dependence on the loudness of the sound. On time, I think it is insufficient for the comprehensive understanding of this problem. However, we analyzed this sound with the program, and you obtained the sound diagram and the dependence of the frequency on the nut silent. I think it is a strong point of your report. It is the answer for one of the questions of the problem. Finally, I would like to come to the conclusion. I think that the problem is solved to some extent. However, it remains a lot of questions, beginning from the mechanism of the sound generation and to the questions about the sound spatial distribution, sound generation from the different points of the balloon, the impact of the elastic properties of the balloon, the velocity of rotation, the pressure, the gas in the balloon, etc., etc. So finally, I present you a list of discussion points to discuss it and to deepen the physics of the problem. Thank you very much. Dear reporter, let us start from the mechanism of sound generation. There is the membrane oscillations and the impact of the elastic properties of the rubber. So not only the direct hit with the walls of the balloon. What do you think about the impact of the rubber?
About the membrane oscillations, I made a rough. I spoke about it a little in the third slide, maybe. the one with the little emission.
And in your experimental setup, when you change the circumference of the balloon, you take another balloon or you take the same balloon with another circumference?
It was the same balloon.
Okay, and
So the difference in properties of the rubber is not so it doesn't affect the
in the pressure of the balloon. So you think that there is a potential for the sound formation?
If it wasn't elastic, the sound will be produced the same.
And what about the second effect of the balloon? There is a resonation of the sound in the balloon, so there are some changing rates in the proper frequencies of the balloon. Maybe there are some impact of these frequencies to the spectrum.
Can you please repeat? I haven't understood the
So the balloon, this is the resonator of the sound, and there are the proper frequencies of the balloon, and maybe it will change the sound spectrum. Yeah?
I don't. Frequency of the sound will change the sound spectrum.
Okay. What do you think?
I don't think it will affect it so much.
Will it affect it so much? Yeah?
It won't affect it so much.
Wonderful, so much. Okay, thank you. And what do you think in general about the sound spectrum characteristics? We have not only one frequency as in this theory, but some range of frequencies and some energy distribution over the frequencies. What do you think? How would be this energy distribution?
This distribution would be kind of well, since there are many harmonics, the sound is not a single frequency, so there are many harmonics that and then the energy of the harmonic decreases with time.
Okay, thank you very much. Your point is clear. Let's move on to the second slide of discussion points. Let's discuss the loudness of sound that depends on parameters. Maybe in your experiment you change somehow the velocity of rotation.
I try to obtain not a same velocity but a same period, because after a certain rotational velocity the spectrum became two horizontal lines and the spectrum went on, off. Or from one extreme to the other. It wasn't, I couldn't find different periods and characterize them.
And from what period the loudness of the sound is higher? So what is the dependence? How to increase or to decrease the loudness of the sound? What should we do?
Increase rotational velocity, or maybe changing the gas container inside of the balloon.
And in your experimental setup, when you have a difference in circumferences, you have the same velocity of rotation or not? 50 seconds left.
More or less the same. So I took different periods.
Okay, thank you very much. And what do you think about your experiments? You rotate the ball with the hand. Do you think that this is essential for the deviation of sound?
The fact that I use a setup stable, it could affect, but I tried, since the balloon was quite clear, I tried to keep it on the main circumference that I measured.
Okay,
so,
and how do you measure the position of the hex nuts? You measure it by video or?
I didn't know that it was around about the same circumference, about the maximum circumference.
So you fix somehow the position?
Thank you for your discussion. We have to go next stage. Questions from the reviewer team?
Yeah. Do you maybe have any photos of your spectrum from the measurement? You plotted some spectrum dots for the first peak. Do you maybe have pictures, photos of those?
I didn't extract them. I have the spectrum of the period as I showed, or the spectrum itself?
For your transform of your sound, right? At some
I have them, but I didn't plot them.
Okay. In Croatia, and I'll be reviewing this problem. So the problem was screen balloon, as you saw. The reporter was from the Italian team, opponent from the Ukrainian team. Now I would like to point out some good and bad points about both of them, about both of their presentations. So first of all, reporter, you had a really good explanation of the problem, and you did a lot of measurements that were consistent and tried to fit them and stuff. But some of the bad points were that, as she pointed out, you didn't have any dependence on velocity, and that seems like an important parameter. So all of your points on your graph were, we don't know, at constant velocity or something, but you didn't measure it or say that. Second, there is no mathematical background, like trying to solve force damage wave equation or something, even though it's really hard to do it. You could have mentioned it, like mathematical background behind the problem. Third, you have no images of the spectrum, which is kind of important, which we'll see, and so we don't know how the spectrum looks like. And you didn't mention a lot of parameters except for the radius of the hexanode and the radius of the balloon, and that's not a lot of parameters, and how they affect other characteristics of the sound. Okay, next, opponent. What I liked is that she pointed out lack of research on the spectrum, so it seems that you only looked at the first peak, first maximum, but didn't analyze other peaks, what do they mean and stuff like that. And the only thing that I have against is that you said that you liked their experimental apparatus, and then, but before that you said that they didn't explain it well, so. Okay. So I have some questions that I would like for us to discuss together. First is energy dissipation in the system. So obviously, as you're forcing the rotation, there is energy dissipation in the system. What does it do? What parameter does it affect the energy dissipation rate in the system? Second, how different shapes of the knot affect, like pentagon, square, circle, or something like that? How it affects the resulting frequency, loudness, and stuff? And what other peaks of the spectrum mean? As you don't have photos of the spectrum, I'll draw it on the board roughly. And question: would other objects scream? And why is balloon so special? Like, if you took another material or something different material, would they produce a sound? If yes, why? If not, why so? Okay, we can move to the first.
I can say one thing about the fact you noted that you said that I didn't noted the fact that I mean vary the radius of the knot. Okay.
No, not radius of knot. Material, like plastic knot.
Before this slide before, you said that I didn't consider the variation of the radius. No, not in slide. Why we were talking?
Okay, sorry. I meant different nuts, different materials and shapes. Not the size of the nuts. Like plastic nut of same size.
Okay.
What we
That the right radius. I
I saw different radius. Yeah, that's okay. So I have a question for both of you, and that's energy dissipation in the system. What does it affect? What parameters? Like frequency, loudness? I don't know. So you.
We have in the system indeed the dissipation, but as we see from the observation, the rotation is still stable. It is stable because there is an energy pumped into the system.
Yes.
Due to the rotation by hand. So there is some shift between the rotation by hand and the rotation of the nut. And this is the mechanism of the energy pumping that compensates the dissipations. So for the stable rotation, only the parameters mentioned, like velocity of rotation, like the position, or so there's a.
Yeah, but I mean, like, where does that energy go? It dissipates at all times. Where does it go?
Yes, of course,
Where
because
does it go?
we have the oscillations of membrane. For each heat, we have the deflection of membrane, and there are some energy of the oscillations of this membrane. These oscillations are subjected to the high jumping. However, we can hear the sound, and there are also the noises of the hex nut. So some losses.
Okay, it's okay. What do you think? How different shapes of the nut affect the results? Like if you took a circle or a triangle or a pentagon, what would they do to the experiment?
Different shape. For different shapes, I used we tried with coin.
Okay.
A little coin that had many peaks.
Okay. And what
so we obtained that the frequency was the tone was really high.
Okay. Okay.
Yeah, like a normal nut, but rotated at high velocity.
Okay.
And we obtained it even if it was not rotated at a high velocity.
Okay. I'll just draw a spectrum.
1 minute left.
Okay. So it looks something like this.
So when we have a different shape of
This is logarithmic scale. This is amplitude. This is frequency logarithmic. So does anyone of you know what other peaks mean? So if you made a spectrum, you said it looks like
The others are the harmonics.
harmonics. Yeah. Okay. So what does the first one? Why are there harmonics?
Can I please say something about the previous question? Because the sides of the hex nuts or the notches produce the sound because when the object is round, there is no screen of the balloon, so the changing of the shape of the nut, for example, the pentagonal or something else, changes the frequency maybe proportionally or somehow like this.
Okay. What do you think would other objects scream, or is balloon special?
Further up, I don't know, maybe it's just a fact that is an elastic surface.
Can you?
Okay. Okay. So general discussion. Does it? Okay.
Maybe my team want to add something?
Okay.
Okay, how many peaks you have in your spectrum, and how does it depend on the parameters of the system? How many peaks? How many?
Okay, can you repeat from the top, please?
How many peaks in the spectrum do you observe, and how it depends on the equivalent parameters of the system?
Of the peaks we saw,
Yes, so it is C harmonic, and
well, we saw the first one that was really high compared to the others. It was a scale that was, if this was the second, the first one was kind of here.
Okay. Why do you think that it was high? The first one was maximum.
Was
Why?
the maximum?
Why?
Yeah,
Why?
the mean frequency.
Okay. So it's like driving frequency, right?
how many such peaks as you you observe in your spectrum?
We saw kind of about 1, 2.
Does
If
it
we
depend-
send it to the infinity going, looking at a really small scale, almost every harmonic, every distance.
And does it depend on the parameters of the system? It's a number.
Yeah, so the first, since the mean frequency depends on the parameters of the others.
Okay,
Also the others.
Okay.
I want to ask a question about your microphone that you used. What is the microphone that you used in your experiment?
We use a microphone, yeah, a microphone.
What was the characteristic? I mean, what was the region of frequencies that it can analyze?
We took with the program. We just selected the region frequency from 0 to 4,000 Hz.
And your microphone was able to analyze the frequency of, for example, 1 Hz.
Yeah. The program. Well, maybe not the microphone, but the program.
That's interesting.
Okay. So
Okay, maybe I have another question about your spectrum with the drone. How does the width of the peaks depend on the parameters of the system and why? Maybe you observed in your experiment that for some cases the peaks are wider than for another.
Since they are related to the frequency, since the magnitude of the frequency is related to the, we found it is related to the velocity. We know it is related to the velocity. So the higher the velocity, the highest the peak.
We have a question from Paul.
So I take it you both took a model for a balloon as a forced oscillator, right? It is analogous to a forced oscillator. So my question is, if you oscillate a Meson spring, if you force a Meson spring, it will have the frequency of the frequency of the force. So here you force the balloon with that hexagon according to our model. Why do you see these other harmonics then, and what are the parameters that you would say why they appear?
It's a question for both of you. Why do other harmonics appear if you're driving it with a single frequency? I think I understood your question.
Yeah.
Why? Well, yeah, the other small harmonics are appearing.
Yeah, why?
It's a normal. It's a normal sound wave. No wave. It's a wave equation that
Okay.
makes.
Is the driving force
solutions.
is the driving force for both of you oscillatory? So is it sine or cosine, or is it something different? The force, is it sinusoidal, or is it something different? Anyone of you can answer?
In the reality, there is firstly a difference between a plate, a membrane, and the spherical one, and secondly, the rubber is not a material with a linear elastic properties. That's why maybe the oscillations will not be exactly sine or cosine. However,
Yes.
there are some small deviations from the zero position. That's one, to some extent, I think we can model it with a simple harmonic oscillation.
Okay, we're finished now, and
Thank you for your discussion. We have to move to the next stage. Concluding remarks.
So thank you both for your comments, and I'm glad. I thank you for your possible suggestions on your team's suggestion on trying to change the gas contained inside the balloon. I didn't put the spectrum since I thought they were they could have been kind of confusing. And thank you.
Now it's time for questions from the jury team. Who wants to start? Vladimir?
Okay, could you please switch to a slide with formulas?
Me?
Yes. Okay. I think
this one?
yeah, this one is normal. I think. Okay, another one where you have new zero, and you have somehow this new zero described it.
Yeah.
Yeah. Could you please explain the physical meaning? Why new zero contains this square root of 3?
It comes from this relation.
And from where does this relation
square
come?
root of 3 is related to the, since I used the white of the nut under the fraction, I was D is the white of the nut, not the length itself. So it comes from the
Okay.
formula of the length.
And from where does it come this bias that you have the another term with the minus sign?
No, wait. I didn't understand.
You have the second term in your formula. 1/2 minus dp divided by c.
Yeah.
From what comes this term?
The minus dpc.
Yeah.
Still from this one, I just took the. Here is the length. I took inside the formula. I put instead of the white over square root of 3. I doubled the white, so it was the second length was 2 white over square root of 3. But so this is the contribute for from the height of the center of the balloon, of the nut. So the distance between the center of the nut and the surface of the balloon.
Yeah, but here we have only one term for distance. It's the same distance, d and d. D there and d here.
Here.
Yes. Okay.
Yeah, but they.
Okay, let's go.
This is the frequency, the main frequency.
I
the one
think
from
it's
before.
too long. Okay, any some other questions? Thank you.
Please, could you go back to slide number 5, please? Yeah, here. Could you explain to me the difference and the experimental condition for the two curves, the two data points?
Why they are different?
Yes. So, I mean, I think the circumference, the diameter of the balloon is different, but what are the parameters? Common parameters.
Yeah, well, the difference in this in circumference, how does it affect? How does it affect?
Yeah, what is the frequency, the rotation frequency of the balloon?
Yeah, it was.
Is it the same? Is it different?
I took many measures and took values that had a similar periods from each other.
I agree, but you are comparing two different sizes for the balloon.
Yeah.
Is the frequency of rotation by hand is the same or is it different? Or?
No, it's different.
Okay. Okay. And so the slide after, so number 6. There are, so you made some change.
I took the axis for the blue measures and I plotted them on the right, so that they weren't in this form.
Okay. You
to show the similar. The
okay,
similar.
you multiply by constant coefficient.
Just transport it.
Okay.
Please.
So it seems to me that velocity of the x is a really important parameter. So it's a question to everybody. How could you control that velocity? Did you control the velocity?
By the frequency of your hand.
Yeah, but just by the human factor.
Well, you can make some. You cannot force a specific velocity, but you can get some velocity and calculate and see what it gives.
Okay.
When you rotate the text you can simply take a video of this rotation and to choose the area where the frequency is constant and to consider this range of your experience.
As I said, I neglected the fact of the different velocities and took same periods, so they had same velocities.
Thank you.
And I think last question. In the statement we have term the scream. How do you understand this term? To all of you, start with reporter. How do you understand the term scream?
It's just the high, probably is the difference between the difference in magnitude between the main harmonic and the others.
You also say that you have a wide range of harmonics that are awoken, so it's not
wide range of harmonics. And Arina?
Maybe the term is related to the frequency of the sound, but I think that my team have something to add.
I think that we have added a video in the statement of the problem, and in this video we heard the characteristic sound, and I think that.
How do you understand the term scream? What is the scream?
So
just
The physics.
high frequency and
Phenomenon.
loud, like loud.
When the high frequencies are
Yeah,
loud.
maybe short answer.
High frequency loud sound.
Mhm.